All right, in this example, we have a fairly abstract function. A is the set 1, 2, and we define the function I, where the domain is A times the power set of A. So the first coordinate is an element of A, and the second coordinate is a subset of A. And the range will be 0, 1, and we'll define it to be 0 if the element of A is not an element of the subset, and we'll define it to be 1 if the element of A is an element of the subset. Okay, first the few easy ones. 1 is not an element of the empty set, and so this is equal to 0. 1 is an element of the set containing 1, so that's equal to 1. 2 is an element of the set containing 2, so that's equal to 1 as well. Okay, now this one's a bit more complicated, and we'll do some scratch work on the side down here. So here I'm trying to find the image of this set. So if I take one Cartesian product with the power set containing 2, that's 1 cross the empty set and the set containing 2. So here are my ordered pairs. I could have 1 and the empty set, and 1 and the set containing 2. So this Cartesian product here has 2 elements. Now to find the function applied to this set, I take the function applied to both of these. So the function I of 1 empty set, that's equal to 0. Also the function of 1 and the set containing 2, that's also equal to 0. So if I apply I to either element, I get 0, and therefore I of this set is equal to the set containing 0. Notice it's the set containing 0 and not the element 0. So the image of this set is some other set. Okay, similar idea for number 5. The Cartesian product of the set containing 2 and the power set of the set containing 2, that's equal to 2 Cartesian product with empty set and 2. And so I get 2 ordered pairs, 2 empty set, and then 2 set containing 2. Okay, I apply the function I to both of these. So the I of 2 empty set, 2 is not an element of the empty set, so that's 0. 2 is an element of the set containing 2, so that's equal to 1. So therefore, I of the Cartesian product of the set containing 2 and the power set of the set containing 2 is equal to 0, 1. Those are my possible answers, and so the image of this set would be the set of the possible answers. Okay, number 6, find the image of the Cartesian product of the set containing A. So this one looks a little funny. We have 1, 2 cross A. So the image would be with the set containing A. So I need an element of this and an element of this. The other way this can happen is an element of this and an element of this. Okay, the image of, if I apply 1A, 1 is an element of A, and so I get 1. If I take 2A, 2 is also an element of A, so I get 1. And so therefore I conclude that the image of A, the Cartesian product of A and the set containing A, is equal to the set containing 1. All right, Number 7, find the inverse image of 1, find the inverse image of 0. For this, probably the easiest thing to do is actually list out all the possibilities, and then we'll construct the inverse images. Okay, so the inverse image. So let's list out all the possibilities. Now, how many possibilities are there? The power set will have 4 elements, 2 squared. The power set has 4 elements. A has 2 elements, so there are 8 possible elements in the domain here. So let's just list them all out and see what happens. The image of 1, empty set. Image of 1, set containing 1. We have 1, set containing 2. And also 1, set containing 1 and 2. Okay, so that's 4 of the elements in the domain. The other 4 elements are going to be 2, empty set, 2, set containing 1, 2, set containing 2, and then 2, set containing 1 and 2. All right, so let's just list these out. That's 0. 1 is not an element of the empty set. 1 is an element of this set. 1 is not an element of that set. 1 is an element of this set. 2 is not an element. 2 is not an element. 2 is an element. 2 is an element. So the inverse image of 1 would be the set of all things that map to 1. So if I list them all out, 1, set containing 1, that's one thing in the domain. 1, set containing 1 and 2. Then 2, set containing 2. And then finally 2, set containing 1 and 2. So those are the 4 things in the domain that map to 1. Things that map to 0, 1, empty set, that ordered pair. 1, set containing 2. 2, empty set, that ordered pair. And finally 2, set containing 1. And so that would be the inverse image of 0. All the things that I of all these things is equal to 0. Okay, so that's 37. Let's now take a look at 38, which is a continuation of this problem. Okay. So we define this new function f, which maps the power set of A into the set 0, 1, 2, 3, such that f of s is equal to 2i1s plus i2s. All right, now this is a little bit abstract, so let's write out the elements. So let's figure out what happens to the power set. Let's figure out what happens to the set containing 1, the set containing 2, and the set containing 1 and 2. There are 4 things in the domain. Since A has 2 elements, the power set has 2 squared 4 elements. So let's see what happens. F of the empty set, that's equal to 2 times I of 1 empty set plus I of 2 empty set. 1 is not an element of the empty set. 2 is not an element of the empty set, so I get 2 times 0 plus 0, which is equal to 0. Okay, let's now map the set containing 1. So I have 2i, 1, set containing 1, and then I of 2, set containing 1. 1 is an element of the set containing 1, so this function is 1, 2 times 1. 2 is not an element of the set containing 1, so that's 0, and so I get 2. Next, we have 2i of 1 set containing 2 plus I of 2 set containing 2. Okay, 1 is not an element of this set, so that I get 0 there. 2 is an element of this set, so I get 1. And finally, f of 1, 2, I have 2 times I of 1 set containing 1 and 2 plus I of 2, set containing 1 and 2. 1 is an element of this set. 2 is also an element. So that's 1. And so I get 3. Okay, now with that in hand, let's now determine this. Is the function 1 to 1? Yes. Different sets go to different things over here. So nothing gets repeated over here, so the function is 1 to 1. Is it onto? That's also onto, because each of the elements in the codomain here get hit at least once. So it is both 1 to 1 and onto, so therefore it is a 1 to 1 correspondence, and therefore it has an inverse. So it's the function is both 1 to 1 and onto, so it has an inverse, and let's figure out what the inverse is. Well, the inverse is pretty much what you see here. So to figure out the inverse, F inverse of 0 would be the empty set. F inverse of 1 would be the set containing 2. F inverse of 2 is the set containing 1. And F inverse of 3 is the set containing 1 and 2. So it's not particularly pretty, but that would be the inverse of this function.